In a previous video, we have discussed the ins and outs of the electromechanical relays. We have learned why we still better use the relays in general, regardless of the great advancements in technology. In this video, let's learn about the other types of relays, the solid-state relays, or SSRs. You'll also learn how to choose among all different types of SSRs depending on a given application. As you see, the look is quite a bit different, the same as its manufacturing technology. Although we're not going to talk about the manufacturing technologies here, and for now, this is enough to know that there is no mechanical moving part and all are made of semiconductors such as diodes, transistors, thyristors, triacs, and so on. There are different designs for different usages. For example, when you're designing the internal layout of an electrical control panel, you always in need of more space. And this relay, as it has a slim design, would be an appropriate choice for you. You can use it as an interface between your PLC output cards and the loads out there in the process. However, as you'll see in the future videos, the thyristors and triacs are more intended to drive the resistive heating elements, and therefore the solid-state relays which use these electronic parts in their output circuits are also more applicable for these purposes. They also have different names depending on the manufacturer. For instance, photorelays, MOSFET relays, solid-state modules, solid-state drives, and so on. I hope you're excited about the rest of the video, so keep watching as there are lots of key practical points to discuss. But before that, please don't forget to subscribe, click the notification bell, and hit the like button. First of all, let's see how an SSR works. The relay we have chosen for this example is a single-phase relay that accepts a fixed DC voltage on its input terminals and has only a normally open contact on its output. As you see, the input is ranging from 3 to 32 volts DC. Let's see what it means. You can check this by doing a continuity test using a power supply and a voltage tester or multimeter to make sure of the functionality of your relay. I adjust the tester for the continuity test and place the probes on the output terminals of the relay. As soon as the input voltage reaches the 3 volts or above, you can hear a sound from your tester, so the electronic output contact has been closed. On the output side, we see that we can connect a 24 to 480 volts AC load. Let's assume that there is a 600 watt 230 volt heater that we want to use as the load, and control the temperature using a control signal coming from a PLC. In a future video, you'll see that SSRs are usually used with another type of controller known as the PID controller. The heater will get its power from the AC power source, but via the SSR. We transfer the live wire to the heater via the SSR. So, we connect the live wire from the power source to one of the output terminals of the SSR, and will wire its other terminal to the heater. The neutral wire will be directly connected to the heater from the power source. Here, you have to make sure to cover the terminals of the SSR as it has electrical power all the time, even when the relay output is switched off. As soon as the PLC sends the command, the SSR LED turns on, showing the output of the relay is closed. So the heater turns on and starts warming up to increase the temperature. Of course, there is a sensor to feed back the temperature of the tank to the PLC. To talk about the advantages and disadvantages, consider a process in which we're going to send commands to a load in a matter of milliseconds. In this process, the speed of switching gets a major parameter for us. So we'll benefit from the semiconductor technology of the SSRs, as they are way faster than electromechanical relays. As you may already know, the millivoltage signals, such as the signals from the thermocouples, can be corrupted by the electrical noise. Whenever an electromechanical relay switches on or off, it produces some electrical noise in the panel. And the more the electromechanical relays are, the more could be the noise and the chance of corrupting our signals in the control system. So we better use the SSRs as they emit far less electrical noise. In a hazardous area, you have to use the SSRs because the generated sparks from an EMR switching could be very dangerous and lead to an explosion. Due to all of these advantages and so many more, we believe you'll see the solid-state relays more and more over time. Apart from single-phase, three-phase, slim, or PCB types of SSRs, they fall into three main categories according to their output switching modes. Watch the rest of the video to get a better understanding of different types of solid-state relays and how to choose them for a given application. The first one is the random turn-on SSR or asynchronous solid-state relay. When the controller applies the control voltage to the input terminals of the relay output will turn on immediately after that and fully pass the current toward the load. The second and the most common type is the zero crossing or synchronous type. What is zero crossing? In an AC sine wave, wherever the wave crosses the horizontal axis, will have a zero crossing point. So in this type, as opposed to a random turn-on type relay, when the input is active, it does not conduct the load current immediately. But the output will wait for the first zero crossing point of the AC load voltage to pass the whole electrical current toward the load. In both random turn-on and zero crossing types of SSRs, when the control voltage is removed from the input terminals, the output will not stop passing the load current until the next zero crossing point of the wave reaches. It is a characteristic of all types of solid-state relays, regardless of their switching type. The third type of solid-state relays are proportional control SSRs and have their own different types. The most common types of them are phase angle and burst fire relays. Proportional control SSRs are used for extremely precise control of the output, especially in heating and lighting applications. In proportional control SSRs, the controller will apply an analog control signal to the input of the SSR instead of a fixed DC or AC control signal. So the control signal could be an analog voltage signal such as 0 to 5 or 0 to 10 volts DC, or it could be an electrical DC current such as 4 to 20 milliamps. The output will vary the amount of the load current depending on the amount of the control signal on the input side. For instance, let's assume we have a phase angle SSR that accepts a 0 to 10 volt signal on its input terminals. The controller applies a 5 volt control signal to the SSR input for transmitting 50% of the power to the load. Then the corresponding output AC voltage will be like this. As you see, the SSR output, which is a triac, has turned on at the peak of every AC half cycle and therefore conducting 50% of the power to the load. As another example, this time we have a burst fire SSR with a 0 to 10 volts DC analog control signal. If the controller applies 70% of the input signal, which is 7 volts here, then the output AC voltage would be like this. Say, from every 10 cycles of the AC voltage, only 7 cycles will pass toward the load. These were the simplified waveform for almost all common types of SSRs. Selecting the correct type of solid-state relay allows great precision in process control. Let's quickly see which SSR is appropriate for which application. For resistive loads like heating elements, the zero crossing and proportional control SSRs are perfectly suited. For inductive loads such as electric motors, contactors, and so on, the turn-on type SSRs are usually a better fit. In a future video, we'll show you an example of a zero-cross type SSR in practice, and you'll understand why it is essential to choose the correct type of SSR depending on your application. That's it. Thanks for watching, and don't forget to click the like button.